Welcome back! Finally, we are going to design a PV system. The learning objective of this video lecture is to perform simplified design of a PV system that is connected to the grid. Simplified design of a PV system can be performed as a first step to check the viability of the design for a particular location. This type of design is aimed to quickly calculate the PV system requirements based on the customer's needs and input. So let's get started. As the name suggests, the grid-connected PV system is connected to the electric grid, which will be discussed in this video lecture. In the next video lecture, we will discuss the design of a stand-alone PV system as well. The grid-connected PV system has a continuous exchange of power with the electric grid via the distribution panel. The grid-connected PV system has these important PV system components. The PV array is an interconnection of modules that supplies the required photo-generated power to the system. The power rating of the array is determined based on the system design. The grid-connected or grid-tied inverter is the backbone of the grid-connected PV system. As discussed last week, it is the inverter that is responsible for not only supplying power to the grid as a current source, but also for tracking the grid voltage and frequency. The grid and the load are usually connected through a distribution panel. The interaction with the grid is two-way, while the interaction with the load is unidirectional. A net meter is also usually found in this type of PV system. A net meter is nothing but a two-way power measurement instrument. This meter takes into account not only the power consumed from the grid by the consumer, but also the power fed to the grid by the PV system. Now, let us look at the main features of such a PV system. What happens when the PV array is producing more power than the load demand? And what if the PV power is insufficient to power the load? Let us understand this in the following animation. On a normal day with the sun out, the PV modules on top of this rooftop are busy converting the incoming irradiance into photo-generated power. The grid-connected solar inverters used in the system are also constantly converting the DC output of the solar modules into usable AC power. The PV system is able to meet the load demand of the household. On a different day, if it's a very sunny day, the PV system is providing much higher power than what the load needs. Under such a condition, the net surplus power is fed to the grid. In most countries, the consumer can offset his electric bills in this manner. This facility is called net metering. You can see that the net meter is reading a net production as the net power is being fed to the grid. On the other hand, on a cloudy day, the PV system is providing less power than what the load is expecting. Under such a condition, the load demand is fulfilled by taking the excess power from the grid. Thus, the net meter registers a net consumption as well. Now we will look at the important concept of system efficiency. We know that PV modules could be as much as 20% efficient in converting the incoming irradiance into PV power. We have also seen how the rest of the system components have less than 100% efficiency. So what can be said about the overall system efficiency? In this grid-connected PV system schematic, you see the various system components. Let's walk through the system to see the efficiency loss at each stage. I will suppose some efficiency value for each component so that we can get a rough estimate of how the system efficiency might look like. Let's assume AM 1.5 irradiance levels and that the PV array is 20% efficient. Therefore, the power density present at output of the PV array is 200 watts per square meters. As the balance of systems could be placed at a considerable distance from the PV array due to the fact that inverters need to be well protected, it might be that the DC power loss in the cables is significant. Depending on the length of the cables and the amount of current through them, this loss could be around 1 to 2%. In this example, let's assume that we have a cable loss equal to 2% of the PV power production, or equivalently, the cables have a transmission efficiency of 98%. Therefore, the DC power per area going to the inverters is 98% of 200, which is 196 watts per square meters. Now, let's go to the inverter. With the advancements in the power electronics, it's rather common to have inverters that reach greater than 97% efficiency. However, usually the efficiency of the inverter is dependent on the power at which it operates. It's seen from practice that the inverters typically reach their rated efficiencies at around 50% of the rated operating power. For the sake of simplicity, we shall assume an average efficiency of 95% for the inverter. Thus the AC power per area present in the system is 95% of 196, which is 186.2 watts per square meters. Assuming a lossless exchange at the distribution panel and a negligible dissipation in the cables carrying AC power, we get an overall PV system output of 86.2 watts per square meters. This means that the incoming E-radius at 1000 watts per square meters is processed by the PV system to give 186.2 watts per square meters. In other words, the overall system efficiency is 186.2 divided by 1000 watts per square meters, which is 18.62%. It can also be said that the overall system efficiency is calculated as the product of the various component efficiencies. That is, eta system equals eta PV times eta cable times eta inverter. Now, let's discuss how to design a PV system. We here use a simplified design strategy that can be applied to both grid-connected and stand-alone PV systems. In this design strategy, only the bare minimum input requirements are known, such as the PV module type, the loads used in the PV system, charge controllers type, inverter type, and the maximum power point tracker. For this simplified strategy, many oversimplifications are applied. These include the use of a simplified load profile and disregarding the location's meteorological effects like ambient temperatures and wind speed are ignored. Moreover, for the simplified design, we simply use the standard test conditions data of the PV modules and therefore do not take into account the sun position or PV module orientation. In this video, you are going to learn about the different steps involved in this design strategy. Let's begin. This method follows a 6-step plan to complete a PV system design. The first step involves listing all the loads in a so-called load table to determine the daily total load demand in watt-hours. A load table basically contains information about the loads that will be connected to the PV system. By filling out the details such as the device type, its rated power and its average daily operation time, the energy requirements of the loads can be calculated. As you may notice, we have used separate load tables for DC and AC devices. The total energy requirement of the respective loads are calculated by multiplying the power rating of the load with its average daily operational time. In this example, we need 840 watt-hours per day of DC electrical energy, 2550 watt-hours of AC electricity. In the case of AC load, there is an additional step necessary to convert the AC energy in terms of its equivalent DC energy. This is done by dividing the AC energy usage by the conversion efficiency of the inverter. We need around 2550 watt-hours divided by 90% is 2833 watt-hours of equivalent DC electrical energy. The final daily load demand of the system is calculated in watt-hour by correcting the value for the system losses that includes cables and inverters. Here we assume the total losses to be 10%. So now we know our load energy demand per day. It is 5192 watt-hours per day. The next step is to design a PV array such that its power output can meet the load demand. This starts by obtaining the equivalent sun hours for the PV system's location. The equivalent sun hours is an important parameter when carrying out the simple design of the PV system. An equivalent sun hour, as you may recall, is defined as the number of hours per day averaged over an entire year that a certain location receives one sun illumination. Note that one sun illumination equals 1000 watt per square meters. We can gather from this figure, for example, that a horizontally inclined panel in India receives approximately 4.5 equivalent sun hours per day. Once the number of equivalent sun hours is obtained, we can determine the total required output power of the PV system array. The output power is obtained by dividing the daily total energy requirement by the obtained equivalent sun hour value of 4.5 equivalent sun hours in this case. This gives a PV array power of 1154 watts. Now the PV system needs to be sized by determining the required total number of PV modules. Let's take the following PV modules as a reference. Nominal power output per module is 420 watts at maximum power point with a voltage at maximum power point of 30.5 volts and a current at maximum power point of 13.34 amperes. To find the size of the PV array, we first determine the number of modules needed to generate the needed power. This is achieved by dividing the needed PV array power with the PV modules power at maximum power point found in the modules datasheet. The calculation shows that in this example we need 3 PV modules to match the needed power. Now I must clarify one thing about the grid-connected PV system. Usually the amount of PV panels or the rating of PV panels need not to be exactly as per the load requirements like it will be for the standalone PV system. We will discuss in the next video. This is because any excess or deficit of PV power can be compensated by the grid that is present in the scenario anyway. This will be not true for a standalone system, as any surplus or deficit of power has to be met with a variation in the storage size, leading to considerable system costs. Consequently, in the grid-connected PV system, it's usually seen that the inverter is sized based on the PV array sizes and not to the load size, like in the standalone systems. The question now is, how should the panels be connected? This depends on the inverter. Here you see an example of possible specs of an inverter. When the 3 modules would be connected in series, the maximum voltage at the maximum power point is obtained and equals 3 times the maximum power point voltage of the module, which is 3 times 30.5 volt is 94.5 volts. If the modules were operating at open circuit conditions, the maximum input voltage of the charge control inverter would see 3 times 38.1 volt, which is 114 volts. When the 3 modules would be connected in parallel, the maximum current at the maximum power point is obtained at equals 3 times the current at maximum power point of the module, which is 3 times 13.34 amps, which is 40.2 amps. In this case, if the modules were operating at a short circuit condition, the maximum input current of the inverter would see 3 times 40 amps, which is 42 amps. Considering the specs of the inverter, the maximum input current is equal to 15 amps, which means that the 3 modules should be connected in series in a single string. The voltage of the 3 modules in series fits within the input range. Next to the voltage and the current, the inverter is sized based on the PV power. So the PV power of the 3 modules of 420 watts is 1260 watts. The inverter should be able to handle this power. As a safety margin, generally the inverter is rated for a maximum of 20% higher than the PV array power. In this case, the maximum power rating of the inverter turns out to be around 1512 watt, which means a 2 kilowatt inverter system will do the job. As a final note, I would like to talk about oversizing the PV system. Now, should or can a user oversize the PV system even if he can meet the load needs for much lesser power? For instance, in the previous example, what if instead of the 1260 watt peak you had installed 2520 watt peak? Well, in simple terms, it is possible. Any excess you produce is sent to the grid. Whether or not the grid operator pays you back for this excess depends on the net metering related policies of the electric utility you are connected to. If your grid operator pays you back for every watt of PV power you pump into the grid, it might look beneficial to oversize your PV system. But then the decision would depend on the system costs and the expected system yields, which in turn depend on the irradiance of the place, module level effects, etc. etc. Thus, there could be quite some optimization that could be done purely at an economical level, which we'll discuss next week. In summary, we have discussed a simplified approach to design and size a grid-connected PV system based on the load needs, the local irradiance data, the specs of the modules and inverters. An overview of all steps is summarized in a very handy table. Please note that a PDF version of all the design steps of this simplified design strategy will be made available to the students for their reference on the edX platform. In the next video, we will look at the design rules for a stand-alone PV system. So, see you in the next video.